Hello students, myself Kiran TR. I am here to teach you an important and exciting topic in science, magnetic effects of electric current. Let's go. Hello students. Today myself Kiran TR is going to teach you an interesting and important topic in science, that is magnetic effects of electric current. As you can see in the name itself, electric current produces magnetic effects. That is, the electric current has the capability and the ability to produce what? Magnetic effect. Just now, I have said to you that current can produce magnetic effect. But what is the proof? In science, proof is very essential. So to prove this, we have a very small experiment which is conducted. This experiment requires a setup of electric circuit consisting of battery. Battery is something which creates potential difference. So there is a difference because of which current flows. We have ammeter A. Ammeter is a device. It is a device which measures the amount of electric current present in the electric circuit. So in this circuit, how much current is there? How will you come to know? Just place a meter. So if you place a meter, we can come to know how much current is present in this. We have resistor R. So what does this resistor do? Resistor stops the flow of current. So if the current is coming, resistor says no, I will not allow you to come. So resistor opposes the flow of charges. So we have R resistor. We have key. Key is nothing but switch. So you can turn on or turn off. And we have A, B, C, D, which is a cardboard. And inside the cardboard, we have placed a magnetic compass. So you can see this is magnetic compass. XY is a long straight conductor, and this entire setup is made up of copper wire, right? So the wire which is used to connect all of it is copper. In this setup, the moment you switch on the key, so you switch on, what happens? Current starts to flow. The moment you switch on, the current flows and there is a deflection of needle in the compass. So the moment you switch on the key, the current starts to flow, and in the magnetic compass, the needle which is stable deflects slightly. So it suddenly deflects. What this shows? This shows that the current which has flown has produced magnetic effect or magnetic field around it. You switch off the key, what happens? Current stops to flow and the deflected needle again comes back to the normal position. We see that the needle is deflected. It means electric current through the copper wire has produced magnetic effect. Now we will move on to the next important topic, which is magnetic field and magnetic field lines. Here you have to take into consideration a very important word, that is field. Right? Now what do you mean by field? It's not the field in which you play cricket or basketball, football or other games. It's not that field. It is magnetic field. Now what do you mean by field here? Field is the space or the region in which you can feel the power of exertion of certain object. For example, I am teaching in a class. Let us consider there are 30 students. The students who are sitting in the last bench can hear my voice. That is, my field of voice can be heard by the last bench if there are 30 students. Now let us say few more students joined my class since they liked it, and there are 100 students. Now I do something. I raise my voice and say with a very high tone and intensity. Now even if there are 100 students, let us say the student who are at the last bench the 100 student last bench can hear my voice. So my field of voice can even reach, can be heard by the student in the last bench of 100 class strength. And mind it, I do not have a mic. I am using my own voice. Now let us say there are 500 students. Now I have reached my max. My voice has reached my max. The student, the 110th student or 120th student who are at the far last, at a longer benches, cannot hear me anymore, right? Why? Because my field of voice is only till the last bench of 100 students. So if the students increase from 100 onwards, my voice cannot be heard. So my field is only till 100. Similarly, the magnet as a field. So if you place a magnet, that magnet as a field around which its force can be felt. When you are younger, in your younger days, you would have done this. You would have bought 20 rupees, 10 rupees wala magnet. Two magnets are there. You bought it together. When you bought it together, you could feel higher force here between both of them. But slowly when you went back and went back and went back, what happened? The force started decreasing. So that means this magnet had a force very strong near to it. As it went on, its force started decreasing, similar to this magnet. So as the space increases, as the field increases, its force decreases. So after certain point, you would have felt that this magnet has no effect on this magnet, no force only. So the region in which this magnet has its force is called magnetic field, right? So we'll come to the definition. The region surrounding a magnet. So you have kept a magnet. The region surrounding the magnet in which the force of the magnet can be detected is called magnetic field. So you have kept a magnet. The region surrounding the magnet, how much region we don't know. If you have a very powerful magnet, might be half a kilometer, its field can be detected. But if you have a 10 rupee magnet, which is very small, it can only for a distance of 20 or 30 or 50 centimeter, it has its force. After that, no force. So the region surrounding the magnet in which the force of the magnet can be detected is called magnetic field. Now, what is magnetic field lines? We have understood field, but what is field lines? For that, we will consider and construct a simple experiment. We will take a sheet of white paper, keep a magnet, bar magnet, north pole, south pole, and we will throw some iron fillings. Iron fillings are nothing but small pieces of iron. So iron, very small pieces, lot of it are thrown inside this paper. The moment you do that, after some time you will see these iron fillings you have thrown randomly, but they settle down in a specific way. You can see here, after some time they have arranged themselves in a specific way. They are not random. Before they were random, but now they have become specific. This specificity, this lines, you can see line, one line, two lines, the lines along which these iron fillings align themselves. So these lines along which these iron fillings align themselves is called magnetic field lines, or we can represent it as magnetic field lines. This concludes the topic magnetic field and magnetic field lines. Now we will move on to the next concept, characteristic or features of magnetic field and field lines. What are the features of this magnetic field lines and field we have just studied? The first character is Magnetic field is a vector quantity. Which quantity? Vector quantity. What do you mean by vector quantity? It has both magnitude and direction. Direction you can understand. That is, if you place a magnetic compass, you can tell in which direction is the magnetic field going or moving, or the magnetic field line is moving. But most of the students have this doubt. What is magnitude? Magnitude is nothing but the heaviness, the quantity. You buy 1 kg potato and you buy 500 grams potato. So which has a higher magnitude? 1 kg potato. So that is magnitude. So in your Diwali days, you burst crackers, right? You burst a bijli pataki, small one. Next, you burst an atom bomb. Boom. And you might have seen in your history classes, there was atomic bombing on Hiroshima and Nagasaki, Japan. Entire city is bursted. Magnitude. So which has the highest magnitude? Hiroshima and Nagasaki atomic bombing. Which has the least magnitude? Of course, your bijli pataki in the example which I gave. So that is magnitude. How much? So magnetic field and field line has both magnitude and also we can see which direction it is. Hence, it is called which quantity? A vector quantity. The second thing, the magnetic field lines emerge from North Pole and merge at South Pole, outside the magnet, and vice versa inside the magnet. So if you keep a bar magnet, North Pole to South Pole. So magnetic field line starts from North Pole. See an example here. So magnetic field line starts from here, right? From North Pole it emerges, it gives birth, from North Pole, and it goes and merges to South Pole, outside the bar magnet. So magnetic field line always emerges from North Pole and merges back in South Pole, outside the bar magnet. But inside the bar magnet, it is vice versa. It moves from the South Pole to the North Pole. Simple. Outside the bar magnet, North Pole to South Pole. Inside the bar magnet, South Pole to North Pole. This entire second can be represented in this small equation. And one more thing you can observe here is magnetic field lines are closed. They are never open anywhere. So it's a closed circle or a closed curve. Magnetic field lines are always closed curves. They are never open. Fourth one, magnetic field lines never intersect each other. So two magnetic field lines will never come and cross each other. Intersection point is not there. Now let us imagine a situation. If there are two magnetic field lines, they are intersecting each other. If they are intersecting each other, if you bring a magnetic compass, this compass was there. If you place the compass, there is one field line going in this direction, the other field line is going in this direction. If you place a compass, now compass will get confused which direction to show. There will be two directions. One is this direction and the other is this direction. So magnetic compass can't show two directions, right? So it is never possible that these magnetic field lines intersect each other. In exams, you might get a logical reasoning question asking why, how, why does magnetic field lines never intersect each other? So you have to answer stating, if they did, it means at the point of intersection, the compass needle would point to how many directions? Two directions, which is not possible. Hence, magnetic field lines never intersect each other. This is the fourth characteristic of magnetic field line. Let us understand the last characteristic of magnetic field line, that is the fifth one. The relative strength of the magnetic field is shown by the degree of closeness of field lines. It is simple. If the lines, magnetic field lines are closer to each other, there is stronger magnetic field. If they are far apart, the strength, the strongness of the magnetic field is less, that is, the magnetic field is weaker. You can understand this by a very simple diagram which I have represented here. Which diagram has the highest magnetic field and why? In option A, what can you observe? And in option B, what can you observe? What is the difference? In option A, you will see that magnetic field lines are closer, right? And in option B, the magnetic field lines are far away. There is a lot of distance between first, second and third magnetic field. Now you have to tell me which has a higher magnetic field. Which option? And it is obviously option A. Option A has a higher magnetic field. Why? Because the magnetic field lines are closer and they are crowded. Therefore, this has the strongest magnetic field, and option B has a weaker magnetic field when compared to option A. This shows that the relative strength of the magnetic field, is shown by the degree of closeness of field lines, is shown by the degree of closeness of the field line. So how close they are? More closer, more stronger; less closer, more weaker. If you love to learn more and need more of these videos, click on the subscribe button and the bell icon next to it. Don't forget to like, comment, share. Love you. See you in the next video.